Now we are going to start with the new chapter, state variable analysis. So what is state variable analysis and what are its advantages as compared to the classical model? That all we will discuss one by one. Okay. So whatever methods that we discussed till now, frequency domain and time domain methods, these are all applicable to linear time invariant systems. Linear and time invariant. This we abbreviate as what? LTI. Okay. So all of the methods that we have discussed, they are applicable only for linear time invariant systems. Whereas state variable analysis, it is not confined to LTI systems. It is applicable for time variant systems also, time variant or invariant. Also, it is applicable for non-linear, and finally also for multiple input, multiple output systems. This is abbreviated as MIMO. Okay. So whereas classical methods that we discussed, those are only for single input, single output systems. Okay. So that is one advantage of the state variable analysis, the first advantage. Another advantage is that when you are finding out the transfer function, you find it out for zero initial conditions. But using state variable analysis, you can make use of the initial conditions as well. So you can write initial conditions can be considered for analysis as well as design. This is unlike the transfer function method, wherein transfer function we only find for zero initial conditions, right? Next, another important advantage is that when you take the transfer function, it gives you only the relationship between output and input. Internally, what is happening in the system? Like for example, there are multiple subsystems, right? There is going to be feedback system, even in forward path system there are going to be multiple systems. Now let us say you want to track what is the variable or the output at this subsystem. Then the transfer function will not give you much information. Okay. Whereas the state variable method, it will help you track the behavior of internal components as well. Okay. Through state variable analysis, the behavior of internal components can also be tracked. Okay. So this is why a complete description of the system behavior is possible through the state variable analysis. Let us now try to understand what is meant by state or a state variable, right? So we know that any control system, it can be described mathematically. Any machine to that matter, right? For example, if you take a motor or a generator, then there will be some equations describing the behavior, right? So what will be one equation if you take a shunt motor? Then V is equal to EB plus IARA. This is an equation that will describe the motor, shunt connected motor. Similarly, any machine that you take, any component that you take, you can describe in a mathematical form, and usually it will be a differential equation. So these used to describe a control system. So we will start from the differential equation. If you consider an nth order linear differential equation, then how can you represent this? You can write it as dn y of t dt n, that is the differentiation of the function y of t of the order of n, okay, n times you are differentiating, plus a n minus 1 dn minus 1 y of t by dt n minus 1, n minus 1th order of differentiation, plus so on till a1 dy by dt plus a naught y of t is equal to some function f of t. Okay. So what are this a n minus 1, a1, a naught, all of these are constants. So you can write where a n minus 1, a n minus 2 and so on till a1, a naught are constants. Now the funda here is to divide this nth order differential equations into n number of first order differential equations. What is meant by a first order? In a first order differential equation, you are only going to have these kind of terms. So that means d by dt of some function. Here we have dy by dt. So it can be some other variable. Okay. So that is our goal. This is a nth order linear differential equation. Now this we want to divide into n number of first order differential equations. Okay, so here only we have one equation which is nth order. We want to divide this into n number of first order differential equations. So how you will do that? We will take this y of t as x1 of t. dy by dt we will take as another variable x2 of t, and so on till d square y by dt square we will take as x3 of t. Finally, we will come to this term. This you will take as xn of t, right? Y of t will be x1. You differentiate once, that means order of differentiation is 1. It will be x2. So like that, dn minus 1, order of differentiation is n minus 1. So the variable will be xn of t. So then what can you write this as? This is going to be d by dt of dn minus 1 y of t by dt n minus 1, right? N minus 1th differentiation function you take and then you differentiate again. Then you will get differentiation of the order n. So now you can write as d by dt of this function is what? xn of t. So you're going to get dxn of t. So this implies that dxn of t plus a n minus 1 xn of t plus a n minus 2 x n minus 1 of t plus so on till a1 x2 plus a naught x1 is equal to f of t. Okay. So you can see what is the order of the differential equation. You have the first order differential equation, d by dt of some variable. So this is the first differential equation that we got, first order. Now further we have taken x2 of t is equal to dy by dt, but what is y? It is x1. So x2 is equal to dx1 by dt. This is the second equation. Similarly, x3 of t if you take, you're going to get d square y by dt square, which will be dx2 by dt. This is the third equation. So on like that if you continue till xn of t. This is what you're going to get dxn minus 1 by dt. So this is going to be nth equation. Okay. So these are all the equations. This is the first equation, second equation and so on till you're going to have n number of equations. Okay. So now we have successfully found out n number of first order equations. So we have achieved this by taking some variables in between. Right? What are the variables? x1, x2 and so on till xn minus 1, xn. These n variables are called as the state variables mathematically. So we will relate it with the control system as well. But now mathematically if you take an nth order differential equation and you split it into n number of first order equations, then the variables that you have taken to achieve this x1, x2 and so on till xn, these are called as state variables. and also the first order equations that you have got, these are called as state equations. Okay, so this is the mathematical foundation. Now we will try to find out what is the meaning of state when it comes to control systems. The state at any time t is equal to t naught refers to the condition or status of a dynamic system at t naught. Okay, so for example, you have some circuit elements here. We have a circuit. Okay, it might have some resistors, capacitors, or even electronic devices, right? Now all of this will have some at a particular time t naught. If you take, then they will have certain amount of voltages or the currents flowing through each of them. Now the state refers to what is the particular voltage or currents through each of these circuit elements at time t naught. That is the state, as simple as that. Okay. Now what is a state variable? So first write down the definition. State variable of a system are a minimal set of variables such that they can describe the system behavior completely for the time t which is greater than t naught when their value at time t naught is known, as well as input applied at time t greater than or equal to t naught are known. As an example, you take a RC circuit, series RC circuit. Okay. Now let us say the initial voltage across the capacitor, let us say it is V naught. The capacitance is C and the resistance is R. Now we will also take a switch. That means at a time t is equal to t naught, the switch will close, and this is the input function you can take as E of t. Now if you want the voltage across the capacitor for the time t greater than or equal to t naught, then what are all the information that you will need? You will need this input function, what is E of t, and also what is the initial voltage across the capacitor, right? If you know both of them, then you can find the voltage across the capacitance, you can find the current through the capacitor, you can also find the voltage across the resistor as well as the current through it. Okay, so that means if you know two things, what is the first thing? The initial voltage across capacitor and the input function. This is initial voltage across capacitor and this is the input function. These two if you know, then you can find out the voltage or current through any of the elements for the time t greater than or equal to t naught. So you can say that these two completely describe, so that means you won't need anything else. These both are enough to completely describe the system, describe the behavior of the system. Okay. Now here this is anyways the input. Now what is V naught? This will be the state variable. So for this circuit we need only one state variable so that we can describe the entire system. That is what is the definition here. You can see state variable of a system are a minimal set of variables such that they can describe the system behavior completely for a time t greater than t naught. Okay, but what is the condition? When can the state variable define the system behavior? When their value at time t0 is known, which is the initial value of capacitor in this case, as well as the input applied for time t greater than or equal to t0. So when switch is being closed at t0, then the input is being applied. So if we know the input, then we can describe the system completely. So that is the understanding of state variable in terms of the control systems. Now one important point that you can see here is, what if you take the state variable as the current through capacitor? Will it serve as the state variable? It will not serve as the state variable. Why is that the case? If you know the initial current through the capacitor, it will not help you get the behavior of the system completely. What you will need is the initial voltage. The initial current can change in the capacitor after a transient, after a change in the circuit. So this cannot be taken as a state variable. Similarly, the voltage or the current across resistor, can it be taken as a state variable? These also cannot be taken as a state variable because they will not give you the complete system behavior. So that means there is a choice of state variable. You have to take certain variables as the state variables, only then will you be able to characterize the system. Okay. So a control system, it can be described by means of its input and state variables. So let us say it has multiple inputs u1, u1, u2 and so on, and also it has multiple state variables. Okay, so how many state variables are there? It will depend on the circuit. We will discuss that a little later. Inputs will be depending on how many inputs we are giving. These are the input variables and these are the state variables. And finally, you will have the output variables y1, y2 and so on. Okay. So this is how you represent a control system in general, which is having multiple inputs, multiple outputs and a certain number of state variables.